We can now introduce our model for the exploitation of a renewable resource. We focus on the fish industry, but of course it can be any industry, such as forestry, for instance. The dynamic of the fish stock is described by, so it's described in discrete time. We could perfectly well do it in continuous time as well. So that at time t, the stock of fish is going to be capital S index t. So that's the total number of fish, say, in the ocean, or fish that we care about fishing. Of course, if we let that population of fish grow forever, or if humans weren't around, then they wouldn't grow infinitely. They would reach some kind of steady state. And in ecology, we call that the carrying capacity of the ecosystem. It's a function of how large the ocean is, how much resources there for fishes to eat, for instance, and we denote it by capital K. Now, the natural growth of the fish stock is what we call a logistic map. It is tau of st, so that's the number of new fish at time t, or at any time. Basically, it's a function of the stock of fish I have, equal to r times st, that multiplies 1 minus st divided by k. So RST here is basically the new fish offsprings that would occur if we didn't have any limit on the ecosystem. So if the fish population was very, very low, so that's and R is just a constant here that multiplies ST. And what happens? Well, the problem is that once the fish population gets too large, then it cannot grow as much as it could before. So there's this retroaction here that takes place. This 1 minus st over k, which basically limits the amount of fish that can be born. Now, one detail I have to point out is that R here is said to be between 1 over k and 3 over k. Normally, I could have written, for instance, R times st divided by k, but this is really just to simplify the notation later on, because you get quadratic terms everywhere otherwise. Why 1 and 3? So if you can try it on, say, your calculator, start with some value, and so for k and for s, and use a r that's lower than 1 over k, then you realize that fishes just don't reproduce fast enough, and they die. The population dies out, disappears. If it's over 3 over k, then it has so the growth rate of the population the growth of the population is very fast, and you can get weird thing going on with the dynamic with multiple values for the equilibrium. We don't want to deal with that, but for the math nerds out there, I sincerely recommend you dig into this logistic map, and especially look on the internet for Feigenbaum's constant. It's a fascinating topic, and it's linked to the Mandelbrot set, and it's extremely, it's one of the most interesting constants in mathematics. All right, so that's it for now. So let's just continue by just asking ourselves. So just think in your head, what would be, for instance, tau of 0? Yeah, that's an easy one. So you substitute s by 0, and you get that it's r times 0 multiplied by this, so it's equal to 0. So what does that mean? Well, it means that if my fish stock is 0, then I don't have any fish eggs or fish offsprings, so it can't grow, so that makes total sense. And now another one, tau of k. What would that mean? Yes, the same thing. Here I would get very many offsprings, but if I'm at k here, then I get 1 minus k over k, so 0. So I'm at carrying capacity, so it means that too many fishes die off, and the population is maintained, and the growth of the fish stock is still 0. So to have a positive growth, I need S to be between 0 and k. So here I have the drawing. So you see that this is what happens. So if you start with a very small population, then your growth is small, and then you can the more your fish population grows, then the faster they reproduce, because this is delta S. So the faster S goes up until this maximum there. That's a perfect balance between the how large the the fish stock is and how many fishes reproduce, and the carrying capacity. But then as you approach k, then again you decrease until you get to k, and then you don't grow. So now let us just think for a while. How many steady states do I have in this model? Just as a reminder, a steady state is, well, first of all, I could ask how many state variables do I have? What are they? State variable is what allows me to describe everything that's going to happen in the future. And here there is really only one state, and it's a neat thing that the letter is S. So S is the only state variable, because that's the only thing that will change here. So it's the stock of fish. And how many steady states do I have? Well, I've already written the answer up there. I have 2. I have 0 and I have k. So if I have 0 fish, then I don't grow. But if I have k fish, I don't grow anymore. And if I'm in between, then I have a positive growth. So S is going that way. Okay. So just as a for instance, what this would mean also is if you have a very slow growing population, like for instance forests, it's easy to plant trees, but it takes a long time for all the ecosystem to come back. So we would represent this by R that is close to 1 over k. But if you had some ecosystem that could recover very quickly, so it would mean that there's a large R. So I don't know, it could mean well, if you have a fish population that grows very quickly, like small fishes, then they can come back very quickly if you let the system by itself. So this is the fish population. Now let's go to the fish industry. So let's make a bunch of assumptions. So first of all, let's say it costs C to rent for a fisherman or a fisherwoman to rent a boat. And here C includes all foregone income from other activities. So it's really an opportunity cost. So what could I earn if I did something else outside of fishing? Then this is all I have to sacrifice to and rent my fishing boat to start fishing today. Each boat catches one small fraction of the total stock of fish. So this fraction is alpha, because of course, if we are at the world level, then one fishing boat shouldn't catch half of the fishes in one day. The number of alpha and C, by the way, are constants because they're just set by the model. On the contrary, here there is the number of boats that are rented, say today. it's going to be written in capital B. And this, of course, is not a constant. So it's something that's going to be endogenously determined in the model. The price level for fishes is small p. So just as a quick question, if you remember your microeconomics, so if the market price is always p, what does that mean for the elasticity of demand? Yes, demand is infinitely elastic. If I want to sell a fish, then the price is p. If I ask for, there's no point for me to asking a lower price. And if I ask a higher price, then nobody's going to want to buy it. So you can imagine that it's a small country and sells at the international stage. The goal of that is, again, to allow us to not think too much about the consumer side or consumer surplus. We can just focus on the industry by itself and the fisherman's profit. By the way, so what is the fisherman's profit? Well, it's going to be a function of the stock of fish. And what is it? Well, it's easy. It's P, price of fish, times how many fish do I catch today? Well, it's alpha times S. And what did it cost me to fish these fishes? Well, it cost me C. All right. So it's quite a simple profit function. And now the question we can ask is, what are the total catches in a day? Well, it's a function of the total boats in the ocean. So we're going to label this H, capital H, for harvest. And it's going to be, well, alpha times B times S. So alpha S is the total catches of one fishing boat in the day, and B is the total number of boats. Finally, we have to assume that if S equals K, so if there is the total number of fishes in the ocean, then fishing should at least be profitable for a fisherman. So what does that mean? Well, it means that the profit, if the stock of fish is K, should be larger than 0. So that means that P alpha K minus C should be larger than 0. All right, otherwise I don't have any model, otherwise nobody wants to fish. And of course, K can be smaller, so it's possible that at some point the profit is too low and then people don't want to fish anymore. Okay, so let's go to the steady state fish stock. So we have the natural growth rate and the catches that allows us to find the net growth rate of the stock of fish. So it's in discrete times, so we'll write it delta st, which is equal to, well, how many new fish would enter the ocean without fishing. So that's tau of st minus how many fishes are caught. So that's harvest at time t. And now we just substitute what we know about these two. So it's delta st equals to, so it's rst times 1 minus st divided by k minus, and now this is alpha b. And boats is not a constant, it's some state variable that's going to be described by the model. So it's going to change over time. So we have to add boat at time t and stock at time t. So the interpretation of this harvesting function is quite intuitive. So of course it's proportional to how many boats are trying to catch fishes. But also, why is it proportional to st and not just a constant, for instance? Well, it simply reflects something quite intuitive, is that if the sea is full of fish, then it takes very little effort to catch all the fishes you want in your boat. Whereas if the sea is almost empty, then of course it's going to take a while to fill up your boat. So last piece of the puzzle we now do is find out what is the steady state. Definition of the steady state: when nothing moves. So here B does not have to move, but of course also S does not have to move. So delta S must be stable. So we write it this way. So delta S, and then it's star because that's the change at the steady state, is of course by definition 0. So now we can just substitute what we have here. So I can just write that this part has to be equal to that part. So Rs star times 1 minus S star K has to be equal, so this is the natural growth rate, has to be equal to alpha B star S star, the harvesting. And what's neat here is we get a nice cancellation because the number of fish in the ocean determines how many new fish are born every year, and the number of fish in the ocean determines the number of catches. So we can simply divide one by the other. So if I want to simplify this, I get the following. So I can divide by S star on each side. Now I get only one S star here. So that's what I'm after. But of course, it's going to be an implicit function because B star is still there. We're going to have to look at what happens in the industry to know how the number of boats is going to change. But now what I can do is, now let's just divide by R on every side, on each side, multiply by -1, and then I can add 1 on each side, so 1, and then this one disappears, and then let's just multiply by K everywhere. So K. So here I get S star, the steady state stock of fish, that has to be equal to K times 1 minus alpha beta star divided by R. Well, actually what we can say basically is that S star is not determined totally, it's a function of B star, so we could even write S star of B star. But of course, our goal is to solve the whole problem. And how do we interpret this? Well, it has some intuitive interpretations. So, well, you can think about it in your head for a few seconds. So, how does well, first of all, how is S related to B? Well, it's an inverse relation because there's a minus there. So the more boats are trying to fish, then the lower the stock of fish in the steady state will be. The higher the steady state quantity K, the carrying capacity is, the higher S is going to be. Alpha, it's the efficiency of fishing. So if each boat catches a lot of fish, then again the steady state number of fish is going to be lower. And finally, R is the how quick the fishes reproduce, and there's a minus, but it's divided there. So the two of them makes for a positive function. So of course, the more fishes are able to reproduce quickly, like if there are sardines, I don't know, then still even if there's a lot of fishing, then we're going to have a higher quantity of steady state fishes in the ocean.